Hi there. My name is Yuege Xie, and I'm a PhD student at UT Austin, and I'm graduating this summer. Today, I'm going to talk about our recent work showing sparser random feature models while iterative magnitude pruning. This is a joint work with Bobby Shi, Hayden Schaffer, and Rachel Ward. And Professor Rachel Ward is my advisor. Well, at first, I would like to give some background of our work. First, let's consider the function approximation with additive models. First, I would like to introduce the function approximation. Let's consider we want to approximate a function f with the data from the dimension to output the value from a set of examples. Let's see x1 to xm, and we have observations yk for each k in the set of index set m, and each yk can be approximated by function fxk plus a noise item, and here the new k is bounded by a fixed value. Uh, Furthermore, instead beyond the function besides the function approximation, we add one more constraint, that is our function fx can be approximated with a linear combination of n features. Let's see, the component function is phi jx, and here our goal is to approximate the unknown coefficient of vector c, where the fx equals to the sum of j from 1 to n cj times the phi jx. That's our goal. And furthermore, we observe in many physical settings, many functions may arise naturally as the sum of functions, as we mentioned, the additive functions, and furthermore, each with the limited variable interaction. That means if our input data x is the dimension, only a few coordinates of the x are interacting with each other. So that's we call the limited variable interaction. And this kind of low order interaction can be embedded in the function phi jx, as I mentioned before, the component function. And furthermore, from previous work, we can also represent such low order interaction with the low order random features, with the phi jx is active equals to the activation function sigma here, uh, map on the mu j times the vector here, and times our variable x, and the function can be written as this, where the wi is the random feature vector, as we mentioned before, with, and here the mu I can represent the low order interaction with the full wi, and also our feature will satisfy either they equals to 0 or 1. And for now, the question here is how can we learn the models with the low order interactions? Namely, we want to find which bi is 0 and which ui is 0 or 1. And there are some like previous works on this kind of question. First, line of work is kernel methods. In particular, the shrunk additive models by Knessy and Yu and Liu. They propose a kernel computation method with additive models, and in particular, Liu and all use the L1 minimization to get sparse shrunk additive models. But in this line of work, we need kernel computation to compute the coefficients we would like to approximate. So this line of work is not computational efficient. And another line of work in random feature models, especially the one by Hashimi, Shi, Chipko, Tran, and Ward, introduced sparse random feature models with coefficient vector recovered using base pursuit. Here, they can also guarantee the L1, they can use the L1 minimization to approximate a sparse model. And there is no kernel computation as that in the kernel methods. So we kind of save the computation from the kernel computation, but there is still L1 minimization, and especially for the base pursuit, it takes a lot of computational course to calculate to get the solution. So our motivation is we would like to ask, can we further improve the computational efficiency to approximate the low order interaction with the sparser random feature model? Motivation for our work is the success of the lottery ticket hypothesis in the model specification. That's the way they do the model specification in deep learning. The work is by Franco and Carbin, 2019. And let me explain a little bit about the lottery ticket hypothesis. So we start with a random initialization of a neural network, and then we train the very large or over-parameterized network to converge. Here, the second block is the network. We have the convergence, and based on the weights of the converged network, we prune low magnitude weights based on their absolute values. So the resulting network is sparser than the previous full connected network. And after that, we rewind the weights to the same initialization we have at the very beginning and do the loop for the further step. So after this iterative process, we can get a sparser network, and that has a similar or even better performance compared to the full connected network we trained in the very first stage. And furthermore, beyond the empirical success, Zhou et al. And other concurrent works also theoretically prove that for the sufficiently over-parameterized neural network with randomly initialized weights, and also absolutely, of course, under some conditions, there exists a sub-network that can obtain competitive performance. So they, beyond the empirical evidence, they prove it theoretically. So inspired by the success of the lottery ticket hypothesis, our question is, can we adapt this kind of iterative magnitude pruning technique to improve the computational efficiency of the sparse random feature work we mentioned before by Hashmi, Ward et al., and learn the even sparser models. So before I introduce our algorithm, I would like to give some preliminary on the definitions of the Q-sparse feature weights and also the Q-order functions, which we will use to construct our model. So the first definition is the Q-sparse feature weights. So for as we mentioned, if the our weight vectors is W1 to Wn, so if we have the support set on each coordinate, we have the dense feature. But if we only sample Q coordinate of this weight vector, we call it Q sparse feature weights. And from the D total coordinates, we can have a D choose Q different interaction with the Q degree of the weights. And also we can define the order Q functions respectively with the Q sparse features. Our order Q functions is just a sum of the such kind of functions which only have Q coordinates interacting with each other for the data. So that's the preliminary definitions we need to know before we construct our algorithm. Um, and then I will move to our shrimp algorithm. It can be divided into two stages. The stage one is constructing. As we mentioned before, we want to draw n total features. The n can be small n times the D2 scale, which is the number of different interactions we can have for the d dimension vector with q sparse features, and we can form the corresponding matrix W here, and then we construct the random feature A with the data times the feature vector and add a activation function in front of it. That's the way we construct our feature matrix. And after constructing the feature matrix, we will do the pruning process. That's our stage two. So for the stage two, just like the iterative magnitude pruning, at the very first, we want to have a convergent network. The way we do it for the random feature models is based on the random feature matrix. We compute the minimum L2 norm solution with the pseudo inverse of the matrix, and we can directly compute it. So that's although the dimension at the very first is high, we only need to compute it once. So the computational cost is acceptable. And after getting the first min norm solution, we have a feature index set, and also the resulting C0 or C naught vector. We do the pruning based on the absolute value as well, the same as that in the iterative magnitude pruning. We sort it and only keep the certain portion of the weights. And after that, we update the feature, the coefficient vector based on the rest of the index set PT, and we do the iterative process until we achieve the number of iterations we want, or the number of features goes to 1, since we start with n features, and for every time we prune p percent of the features, the iterations will be finite. And our output will be the set of the pruned minimum L2 norm estimators, and also the feature index pair sets. The question is, after getting those kind of solution sets, how can we choose the model we want from the pruned sets? Will it have the similar performance or even better performance as the very large model, as the original large model? The way we choose the best model is by a validation data set. So we calculate the performance on the with the different estimators on the validation data set, and we choose the best model according to the validation performance. And for the test performance, we just use the best model to evaluate on the test data set. So for this kind of process, we can draw the connection to the neural network pruning. So for the neural network pruning, we can divide the pruning process into two categories. The first one is the weight pruning. That means we only keep some weights between the two layers, and the gray part is the interactions we discard. So we have like sparse connection between the neurons. And for the neuron pruning, we will remove the whole neuron, and the weights connected to the neuron will be moved at the same time. And if we combine these two, we can get a subnetwork after the weight and the neuron pruning. And that's what we can get from shrimp as well. For shrimp, the stage one, when we construct the low order interaction model, it's equivalent to we only keep a few weights here after weight pruning. And for the second part, we have a sparse coefficient vector C, as we mentioned before. And in that resulting model, it's equivalent to neuron pruning. So the two-stage process, the first one is we can draw the connection to the weight pruning, and the second process we can draw a connection to the neuron pruning, and the combined process we can view it as a combination of weight pruning and the neuron pruning. And the formal definition here is formal definitions are listed below. So we first we consider the two-layer fully connected neural network. Where each WI has a full dimension, and we have AI. And for weight pruning, we add some sparsity to the weight WI. And for the neuron pruning, we add sparsity on the coefficient vector. And for our shrimp model, as we mentioned, we can view it as sum of the low order component function, and the sparsity is obtained both on the weight vector and also the coefficient vector. And furthermore, we also list some properties of shrimp and other sparse model vector sparse models from two lines. The first is the sparse kernel methods, sparse trunk kernel methods, and also the sparse random feature models. And as we can see from this table, shrimp can obtain both the sample sparsity and also the feature sparsity due to the two-stage process, and it can obtain the low-order interaction. I forgot to mention the sample sparsity is from the benefit of the sparse random feature model, and the low-order interaction and the feature sparsity are from the two-stage process. And from this process, we can obtain computational efficiency since we implicit compute the L2 minimum L2 solution, and we have the decaying number of features we need to deal with during the process. After introduce the formulation of shrimp and the comparison with the other sparse random feature models, I will go through the empirical results and also corresponding theoretical understanding of shrimp in the following talk. So first is the experimental results. We first evaluate different methods, the sparse random feature methods by Hashmi, Ward and all, and also the plan minimum L2 solution and the state-of-the-art method SALSA on the synthetic functions. Those functions are either simple additive functions or the functions which are used in the previous works. And also we in these experiments, we mainly focus on the low order interaction functions. And as we can see from this table, for both low dimension or high dimension function approximation, shrimp can obtain the best test performance over all the methods, especially for the very simple additive functions. For example, the F2 function, we can obtain magnitude better or way better performance, and also obtains the average size, which means how many coefficients are left in the resulting model. So the resulting model is very sparse as well. In this synthetic experiments, we can verify the better performance and also the sparsity of shrimp compared with other methods. And beyond the synthetic function approximation, we also evaluate shrimp on real-world data sets. So this table shows our performance on 8 real-world benchmark data sets from the UCI repo. And those are from the real-world data sets, either from the physical systems or some interesting data set like the housing. So for those data sets, we also compare shrimp with the SALSA, SSM, SSM, and LASSO. And for the first 4 data sets, we can obtain the best methods over the 4 methods and the best results over the 4 methods. And also for the rest of the data sets, we can have the competitive and very close test error on shrimp compared to other methods. And I would like to mention those methods from the previous methods are directly taken from their paper. So we assume they tune the model and get the best results of their methods. And also we have application on the robotics data estimation. We use the data from Wei, Hot, Delig, and Biswas from the robotics data. The task is to estimate the position of some vehicles, also the angle of the vehicles and their velocity and angular velocity. We compare those estimations and both the training time and the inference time of shrimp and the SALSA. The reason we do it is because we find in previous results, SALSA can obtain some good results as well. So we would like to compare the shrimp with SALSA in more experiments to see the performance. And we can see for the position and the angular estimation, we can obtain better results. And we can also obtain similar results on the rest of the measurements. And for the training and the inference time, we can obtain way better training and the inference time by shrimp. That means we can spend less computational cost to get a sparse random feature model by shrimp. And during the inference time, the reason people want sparse model in practice is when the large amount of data coming, we want to do the inference very quickly, like we do it on the mobile phones, or like we do the streaming inference on the servers. So the inference time is a crucial efficiency measurement in practice. And also we beyond this comparison, we also illustrate the time complexity comparison with shrimp and the L1. The L1 is just the SRFES here, and we compare that with the increasing number of features and with different dimension and the number of data. We can see the solid lines are shrimp, so that's much lower than that of the SRFE, which need the base pursuit to get the sparse function approximators. And also we compare with SALSA with the increasing number of data, and with since the SALSA is a kernel-based method, it doesn't have the varying number of features. So we compare that with a varying number of data and with very different number of features for shrimp. So we can see that's also for both training and inference time, shrimp obtains better training and inference time than SALSA with the number of features as 200 and 2000. But I would like to mention here, if we have a very large number of features for shrimp, we can see the training time is slower, will become slower, since we can see from this figure, as the number of features increase, the training time will increase. But the inference time will stay very similar since the resulting model is sparse. So the inference time is only related to the resulting sparsity of the final model. So it has nothing to do about the initial number of features. And also, we can see the robustness to the pruning rates. From this slide, we would like to evaluate because for shrimp, we need to input a fixed ratio for the pruning. And if we vary the pruning rates, if we can get similar results for like a range of pruning rates, instead, if we need to tune the pruning rates very carefully, so in practice, it will take some efforts. It will take some efforts on it, and as we can see from this figure, for real-world data sets, we can see the robustness to the pruning rates for both the test SME and the basic Q chosen by shrimp. And I would also like to introduce a very surprising or interesting finding of the supporter recovery and feature selection obtained by shrimp. In this case, we do the we perform shrimp on a very simple function fsx with the owning additive owning the sum of the cosine and the sine functions and on only order 1 coordinates. And we can see at the very first, we have the number of the features is 20K, and there are some weights distributed on the unrelated or the coordinates we don't want it. And after the pruning, the weights on those coordinates will disappear. And here at the resulting model chosen by shrimp, we have only 38 number of features, and all those features are distributed on the coordinates of interest, and we don't have other features, not other coordinates that don't appear in this function. So in that case, shrimp can do the supported recovery and also the feature selection during the pruning process. And beyond this, we want to the question we would like to ask is if we do the random pruning without rewinding and without the iterative process, can we just train on certain number of features and will that kind of model obtain the similar or better results than shrimp? So do we indeed need the iterative magnitude pruning? So we compare the SRFES and the planned minimum solution, which corresponds to the random pruning here. And as we can see, the blue lines in those plots, shrimp can obtain the best test MSE in all the examples. And also here we also see some double descent curve here. And also we have the resulting model is sparser than other models. And I think those are the empirical findings of shrimp. And to explain the success of shrimp and also shed a light on the understanding of the iterative magnitude pruning in neural networks, we also provide some theoretical explanation. So all those theoretical results are refined analysis to the Hashmi et al., as I mentioned before. So first, we have a generalization bounds for the threshold-based pursuit under the similar setting in Hashmi et al. And I won't put explain too much about the every term in those equations, but I would mention like the difference of our refined analysis compared to the generalization bounds for the in Hashmi et al. Is first we connect the numerical results on the maximal singular value of A. As you can see the term here, we have the explicit expression on the singular on the eigenvalue of A transpose A. That corresponds to the singular value of A. And also we demonstrate that a smaller maximal singular value indicates a better generalization. And I will talk about that we also have expectation bound on the grammar matrix, the eigenvalue of minimum and maximum eigenvalues of the grammar matrix as well. And the second, we remove the explicit dependence on the number of features. And here, assuming that we have the ground truth model is as sparse. So here, the results doesn't depend on the number of features, but depends on the eigenvalue or eigenvalue of the grammar matrix or the singular value of A. And also for from the theorem of 5 in our paper, we also have a corollary about the order Q functions. So the first one is for the general function, and specific, especially for the order Q functions, we have order here, and you can find the explicit expression in our paper and also the corresponding proof. And I would like to mention we improved the generalization bound in the SRFES in Hashmi et al. And we also remove the dependence of the number of features to the sparsity level. We change that from the number of features to the sparsity level S. So that's our improvement in the theoretical explanation. And as I mentioned, we have the theoretical the bound depending on the eigenvalues. So we also we also plot the empirical eigenvalues of the grammar matrix and try to understand the benefits of shrimp. Here we can see the yellow line is for the random pruning, and the blue line is for shrimp. And with the low variance case, the shrimp has a decaying maximal eigenvalue. And from our bound, we can see if the eigenvalue is like decaying, we can have a smaller generalization bound. But for the random pruning, it stays similar. So we can see this benefit of shrimp from the perspective of the eigenvalues of a grammar matrix. And we provide some explanation from both empirically and theoretically. And also we have the explicit or theoretical bound on the grammar matrix. The bound is based on the work Dr. Chen mentioned before in last talk. You can refer to that one. We inspired by that work, we proved the expectation of the maximum eigenvalue and the minimum eigenvalue of the grammar matrix. And we also in the special case using Markov inequality, we can have explicit order bound of n, and also some parameter corresponding to the noise level here, and also the Q low order interaction. I would like to mention like we observe like the benefits of small q, that is the low order interactions. So if that's with the order 1, so we can see the benefit of the small q. But if q goes to infinity, goes to d, which means in high dimensional case, we have the full interaction between all the coordinates of the vector. The minimum eigenvalue will become arbitrarily small. So that will lead to the system become become lead the system to become yield conditional. So that's not the case we want. Uh, so above are some theoretical understandings from the perspective of the generalization error and also the found on the eigenvalues of the grammar matrix. So that's provide some insights that why shrimp can have the better or comparative performance than the original fully connected network and have very sparser estimator. Uh, we hope the connection will shed some light on the iterative magnitude pruning in neural network as well. So those are some takeaways. First, we propose a two-stage algorithm SHRIMP to learn the sparse random feature models with low-order interaction, while the successful iterative magnitude pruning technique in neural networks. And it is surprising that the L2-based SHRIMP can find sparse models even than the base pursuit in previous work. And our experiments on both synthetic and the real-world data sets verify that shrimp can obtain better or matching test performance compared to existing state-of-the-art models. And it can obtain computational efficiency and being scalable to high dimensional settings. And we also offer a refined analysis and provide some theoretical understandings. And by connecting shrimp to the process of finding lottery tickets, we want to shed some light on the successful performance of the iterative magnitude pruning in neural networks as well. So those are some references I mentioned in my talk, and thank you very much for listening. And I feel free to ask any questions if you have. So I would be very happy to answer any questions and get feedbacks from you.